Right. Thank you.
Okay, this is my first slide, and I will move on. These are the things I'm going to be talking about. My slides will be made available, of course. Acknowledging my colleagues, Gary and David Woods at Ohio State University, and also Shane Mueller at Michigan Tech. I'm very honored to work with them. So a little bit of background. The notion of human centering can be traced back quite a good ways. Actually, I think it can be traced back to industrial psychology post-World War I, but that's another story. And there's been lots of discussion about it. The phrase human centering originated at NASA Ames in the 1990s, and the ideas of this and the history of it are available. I'm going to focus on the notion of human-computer interdependence as opposed to human-computer interaction. The notion of interaction can be traced back to the Fitts list post-World War II, which described the things that humans are good at versus the things that machines are good at. And clearly the emphasis was on the ways in which the machine compensates for the human. The machine is not subject to emotion or failures of memory or any of those things that characterize the human. And so the idea is that the machines compensate for the human limitations. But a richer view is human-machine interdependence, which focuses on the things that machines are good at and the ways in which they depend upon humans in joint activity, and the things that humans are good at and the ways in which they depend upon their machines. With regard to trust, I think it's important to understand that it's not a state, it's not a single state, it's a very dynamic thing. People often refer to it as if it develops, but it doesn't, it morphs. It can come and go very, very quickly. It's a complex, dynamic relationship. People always feel some degree of justified and unjustified trust in the machine, and justified and unjustified mistrust in the machine. I spent the better part of 40 plus years of my career doing cognitive task analysis with experts in various domains, and I've been asking them, do they trust? Yes? I've been asking them if they trust in their computers, and the response is always a bit of a chuckle. Of course they don't. They'll trust it to do certain things well under certain circumstances, but not do other things well. And we can all see that if we introspect about our relations with our own software systems. Okay. Automation is not autonomous. It's very carefully stated. And it's important for people to understand this. Whenever the word automation is invoked, some people automatically jump to the conclusion that the system is autonomous, and it never is. There are no autonomous machines. They depend on us very, very much in a lot of different ways. Machines outperform the humans. This feeds that mythos, assuming that efficiency is the same, means the same for machines as it does for humans. In the case of weather forecasting, which I'm going to be referring to in this talk, the voodoo is that computers generate forecasts, but they don't. Computers do not generate weather forecasts. They generate specific kinds of point predictions. And talking about it as if computers generate forecasts sets up the man versus machine competition. And one of the things that I saw a lot in weather forecasting, and we've seen this in many, many other domains, is that the practitioners will say, well, gee whiz, our data are limited and they're noisy and messy. And if all we need is more data, and if we have more data, we'd be able to solve all these problems. But what results is data overload, which is used to justify the need for more processing systems to process all that wonderful data that we just got. And then another piece of voodoo thinking is all we need is more computer power, and then poof, a miracle is going to occur, and we won't be able to need the human at all. And I see all of these things in the field of weather forecasting. I'm sure you all have seen them in domains that you've looked at. There are a number of reactions that I find that forecasters have had to this idea of emerging AI systems. One reaction is dismissive, forget the machine, I don't trust them, I go with my gut. I've got my intuitions. Another is resistance, fear that they'll be replaced. Another is somewhat hesitation, cautious hesitation. That might be useful, so I'll check it out and see what happens. And then finally, acceptance. It might be understandable and reliable, but that doesn't mean I need to be complacent. And as the saying goes, we need to trust but verify. Lots of models in weather forecasting. Nearly every forecast element can be represented. Presentation methods vary. Heat maps, real heat maps, probability matched mean, warning cones, all of that sort of thing. And there are just dozens and dozens and dozens of models that are out there. And what happens in practice is the forecaster will start with a base model of the most recent outputs plus the new observations, and then adjust the model outputs based on local knowledge, observations, bias corrections, things like that. Forecasters have to understand the concepts, benefits, and limitations of the models in order to properly interpret this information for decision makers and the public. Where can humans improve upon the machines? Well, humans always correct the machines when they get misaligned with the world. That always happens, and this is a primary way in which automation is not autonomous. Is it always worth the cost? Yes. And what about the risks of not letting the humans improve the machines? So these are other concerns that have been raised in the domain of weather forecasting. So again, computer models do not generate forecasts. A forecaster cannot generate a good forecast with using the models unless he or she can generate a good forecast without using the models. The human is always involved, even the machine, when the machine is doing things in a so-called autonomous way. We never blindly trust them. We're always monitoring. We create workarounds when something goes amiss, and so forth. A lot of this is detailed in one of my recent books. This is the interdependence analysis. This is what we've called the unfits list. And I invite people to meditate on this. I'm not going to dwell on it right now, but you notice it's a broken symmetry. Instead of talking about the grand capabilities of the machine that compensate for the inglorious fallibilities of the human, we're talking about ways in which machines are constrained and ways in which they need people in order to deal with those constraints. And then conversely, ways in which people are not limited, and yet they create machines in order to help them in certain ways. Macrocognition is, as Gary Klein has defined it, the adaptation of cognition to complexity. And so that's why I often refer to all of this as the study of macrocognitive work systems, rather than just human-machine interaction or interface design or any of those things. They're all an important part of it, but there's this broader view of work system design. And there are some classics in psychology that can be cited as forebears of this idea. I won't go into the history in detail. This is one of the models, macrocognitive models. You'll notice right away that it's not an input-output model. It is very different from traditional models based on causal chains and the style of information processing theory, but it has different uses and different purposes. This describes the sense-making process. And the important thing to know about this embedded loop is that the data that you have allow you to create a frame for understanding the data, but then the frame defines, connects, and filters the data. So you're always reframing while you're trying to understand the data that you have. And these loops over here describe that reframing process. This is a similar model for what's called flexecution or flexible execution. This also comes from Gary Klein. And the idea here was, I think, really quite remarkable and important, which is in complex work systems, you're pursuing goals, but at the same time, you're revising them. At the time this was formulated, most of the AI planning systems assumed fixed goals, although there were some exceptions to that assumption. And this I think was quite a remarkable insight. There are other macrocognitive models that describe things like the development of expertise and teaming and so on. And I can provide all of those models with people and the papers where some of this stuff has been written up. Macrocognitive work systems are constrained by certain fundamental bounds. One we call bounded cognizance, which is not unrelated to Herbert Simon's notion, although it goes quite a bit beyond it. There are gaps in fitness, which we refer to as bounded ecology, gaps in perspectives, which we call it bounded perspectivity, gaps across roles, and then finally gaps in, oops, sorry about the typo, gaps in progress. Each of these fundamental bounds goes along with a set of laws, and we have rostered a great many of them, especially Dave Wood's, based on his research. And these are just two of them, which I threw in here because I knew that they would resonate with Ben, because they deal with interface design, Sacagawea law, that the work system must support active organization and exploration of information, and then the Lewis and Clark law, which is that the guidance provided by the machine needs to be shown in a way that is organized in terms of their goals. There are a considerable number of other laws, and again, I can provide people with material that goes into some more detail about this. Now, what I want to focus on quickly now to bring this to a climax is the research foundations of how do we study macrocognitive work systems, how do we evaluate AI systems. And what I see going on right now is that the major programs, which are primarily led and directed by people on the computer science side of the house, they tend to jump right in and create design studies with large sample sizes. Everybody loves Mechanical Turk. That's changing now because of the constraints that we're all experiencing, and there are good ways and not so good ways of doing that. We certainly don't want to just do it because it's easy. People jump right in and design complex factorial experiments. Lots of mindless statistics, worship of P less than 01, Cohen's alpha, etc. And I could fill a whole day's worth of presentation just about that. Search for the holy grail of statistical significance. Assume that users digest and understand the explanations the same as the researchers do, and a lack of consideration of the important control conditions. And so on the right-hand side of this table, you'll see some ideas about how the current research paradigm might be improved. In the cognitive science, computer science approach, the researcher defines the task. They put themselves in the shoes of the user and assume what the user needs. The work is thought of as a set of tasks. The researcher builds a model of the task, and the task is considered independently of work context. And again, on the right side, you see some ideas about how that paradigm might be improved. In the current paradigm, the task is defined independently of the users. It's of low ecological relevance in many cases. There's little or no user testing or usability testing. The system is evaluated using analytic methods, and the system is thought of as a decision aid, but it really ends up being a process control system. And again, on the right-hand side, you can see some ideas about how this paradigm might be improved. Gary referred earlier to what's been called participatory design, that is having users be a part of the design team from the very beginning. The psychology paradigm also needs to change. The current paradigm is situated in the traditional academic laboratory. College freshmen are the subjects. Toy problems lasting the duration of a college class. Again, a lot of mindless statistics. Rigor mortis from over design, which means the experiments go on and on and on. Oh, you failed to control for X, we need to do another experiment. And that is not a good thing. You need to be able to put a stake in the ground. And then traditional psychometrics, which is also a paradigm. It has its values, but a lot of that paradigm doesn't apply in the situations that we're referring here. And then finally, and this was why I titled the talk the way that you see it in the agenda, but more subsequently, and that is, I see an opportunity to fix the procurement process. In the DoD procurement requirements, it says that there must be a human factors evaluation. Well, that's weak. It's possible for the human factors evaluation to be lacking in rigor significantly. And the focus is on safety and survivability and manpower requirements. Those are all important, but there's a lot more to it. And so I've advocated for some years that this particular passage in DoD 5002, if this were rewritten to say deliverable technologies, sorry about that comma, another typo, must be accompanied by convincing empirical evidence that they are understandable, learnable, usable, useful, and that the work can be observed after delivery in order to empirically study how the new technology changes the work. If this were to be a part of the DoD procurement requirements, we would see a lightning change overnight. The big box vendors would go kicking and screaming, but I think in the long run, it would help us achieve the goal that Ben has set out in his definition of human-centered interaction. That concludes my talk. If anybody wants any of this stuff, send me an email. I have sent my slides to the Maryland folks and they will be available there. Thank you.